All right, so with today, we've introduced logarithms, we've now looked at logarithmic functions, and we've looked at transformations of those logarithmic functions. What we're going to look at in today's class is laws associated with dealing with logarithms. Okay, so just like we had exponent laws, right, when you were dealing with multiplying or adding or subtracting or dividing, power over power laws, all that stuff with exponents, we have the same similar type of laws with logarithms. Okay, so we're going to briefly go through them and we're going to spend more time just looking at the examples. So the first one is actually called the product law. And it's kind of the opposite of what your exponential law was, right? So with exponents, if you had, let's say, 3 to the power of 6, and you were multiplying it by 3 to the power of 4, what did you do with those exponents?
Multiply.
You added them.
Wow.
Right? So this would then have been 3 to the power of 10, right? And we talked about how logarithms are the inverse of exponents, so it's kind of the inverse thing happening here. Where here, if you are adding, right, if you are adding logarithms with the same base, what you end up doing is multiplying the arguments together. Okay? Just like how your exponent laws only worked if the base of your exponent was the same, it's the same thing with logarithms. These laws only work if the base of the logarithms are exactly the same. Okay? And in this one, when you're adding the logarithms, you multiply the arguments together. Okay, so in this example, if I have log 3 base 2 plus log 5 base 2, they're both log base 2. So I can apply this law of logarithms and multiply these arguments of 3 and 5 and turn it into a single logarithm of log 15 base 2.
Why is it log prime C?
That's just a typo. It's like a glitch in writing. Okay? All right, your next law is your quotient law. Okay? So again, just like how in your exponent laws, you would have had something along the lines of if you had 3 to the power of 7 divided by 3 squared, what did you do with the exponents? You subtracted them, and this would have become 3 to the power of 5. Again, with this inverse operation, what happens here is when you are subtracting logarithms with the same base, you divide their arguments. Okay, so for example here, if I have log 20 base 5 minus log 10 base 5, again, they're both base 5, so I can apply the law of logarithms, get a single log, base 5, where I do 20 divided by 10 and get 2. Okay? So when you're adding logs with the same base, you multiply the arguments. When you're subtracting logs with the same base, you divide. Okay? So that's one way of thinking about it. The third and final law is the power law. So again, if you remember your exponent law with power over power, that's where if you had 3 to the power of 4 all squared, when it was a power of a power, you multiplied your exponents, right? And then that would become 3 to the power of 8. What happens with logarithms is that if you have an argument that has an exponent, right, so in this case, m to the power of p, what you can do is take that exponent and bring it out front, and it becomes then the coefficient of the logarithm, so that's p log m base c. Right, so for example here, if I have log 6 squared base 12, this 2 moves out front to be the coefficient, and instead I have 2 log 6 base 12. Or you can work backwards, you can take a coefficient and bring it up and have it turn into the exponent of that logarithm. Right, so that's another law of logarithm there with the power law. Okay, so you can move exponents. When you're adding, you multiply the arguments. When you are subtracting, you divide the arguments. Okay, so let's take a look at trying to simplify some of these here. So in this first one, we've got log xy divided by z base 5. Okay, what it wants us to do is write this as an expression in terms of individual logarithms. So it wants 3 different logarithms, something with log x, something with log y, something with log z, that would fit this rule. So what operations are happening in this argument of xy divided by z? Well, there's a division, right? xy is being divided by z, which means we can use that quotient law, which means we can write it as log xy base 5 minus log z base 5. Right? Because that law of logarithms is that when you subtract logs, you divide the arguments. Okay? So now I still need to split up this one. What operation is happening between these? It's multiplication. So with logarithms, I turn that into addition. So this is now log y base 5 plus log x base 5 minus log z base 5. Right? So when an argument has two factors that are being multiplied, you can split them up into separate logs that are being added, and when divided, you can split them up into separate logarithms that are being subtracted. Okay? Let's try b here. Log the cubed root of x base 7. So it might be helpful in this situation to rewrite this argument. What is another way of writing the cube root of x? X to the power of 1/3. So this is really log base 7 x to the power of 1/3. And which logarithm law applies here? The power one, right? Where this exponent can come down and become a coefficient, and instead I'm just left with log, or 1/3 log x base 7.
Would that be like a function?
Right now this is just an expression because it's not equal to anything. I'm just rewriting it. This could be an example of a function if it was y equals that, and then you could graph it. Right now we're just trying to use the laws to rearrange what it looks like. Okay? All right, let's try C. Here we have log 1 over x squared base 6. So again, we can see here that this is a quotient, right? A numerator and a denominator, which means I can rewrite that out using subtraction, where it's log 1 base 6 minus log x squared base 6. Now, something to keep in mind here. Anything log 1 is going to be equal to what? 0. Because anything to the power of 0 is going to equal 1. Right? So this is an actual value that can be evaluated, and it's evaluated at 0. And then in this expression here, we can again apply that power law, and this 2 can come down and be a coefficient. So it's 0 minus 2 log x base 6. So ultimately this simplifies to negative 2 log x base 6. Right? And that would be your simplified expression for C. Right? Finally, you can take a look at D. We have log x cubed over y root z. Now I don't see a base there, so what can I assume the base is? 10. Right? So if we don't see the base, it's assumed that it's just base 10. Right? So again, there's a lot of different things going on in this one. I typically start by splitting up the numerator and denominator. I start with the subtraction, and I would rewrite this as log x cubed minus log of y square root z. Right? This log x cubed, again, I can apply that power law, and it would become 3 log x, right? Because that exponent can come down and become the coefficient. And then I'm going to split up this, because these are two factors, so I can split that up into log y plus log root z. But what's another way I can write root z using exponents? Z to the power of 1/2. Okay? So this is now 3 log x, and now I'm remembering to distribute that negative across, minus log y minus 1/2 log z. Right, so that's just...
I don't mind.
Isn't z to the power of 1/2?
Yeah,
Oh, you just-
yeah, so I distributed this negative across, right, because it was minus the whole thing. Okay, so those are the laws of logarithms being used to simplify an expression. Okay, so now you again can use the same thing, but now using actual values to evaluate them. Okay, so in this first case, we've got log 8 base 6 plus log 9 base 6 minus log 2 base 6, and what we want to do is simplify it to a single logarithm and then evaluate. So what are we doing in this first operation? Right, we've got log 8 base 6 plus log 9 base 6 minus log 2 base 6. Okay, and I've already heard the answer. We're adding logs with the same base, so we multiply the arguments. So this is now log base 6 of, what's 8 times 9? 72. Right, and then we're subtracting log 2 base 6. Now, when we subtract logarithms with the same base, what do we do with the arguments? We divide. So what's 72 divided by 2? 36. So log 36 base 6. And that can now be evaluated. This one we don't need a calculator for, because if you remember, this is essentially 6 to the power of what equals 36? 2. Right? But if you wanted to, you could evaluate on your calculator log 36 divided by log 6 and get an answer of 2. Right? By just remembering how that applies to exponents, that's essentially 6 to the power of what equals 36, and obviously that's 2. Okay? Let's just do one more. Do you want to do B or do you want to do C? C. Of course we do. Okay, so if we did C here, and we've got 2 log 12 base 2 minus, all in brackets, log 6 base 2 plus 1/3 log 27 base 2. Right, so obviously, apply your order of operations. Do the evaluate within the brackets first.
Like for the 1/3 log 27, you could just make that log 3.
Yeah, exactly. So this 1/3 log 27, so we'll just leave this first term here alone, right? We're essentially applying this power law, right, where this 1/3 is going to become an exponent. And I'll just show that intermediate step here. So that's going to become plus log base 2, 27 to the power of 1/3. Well, 27 to the power of 1/3 is the same as the cube root of 27. What's the cube root of 27? 3. Right? So that simplifies already. So now it's...
to know that log 27 to 1/3, the 2 is...
No, I'm just saying that 27 to the 1/3 is 3. Right? Not the evaluation of the log, but just what the argument would become. Right? So then, again, now we can evaluate what's there inside those brackets. We're adding logarithms, so what do we do with the arguments? We multiply them. So we have this 2 log 12 base 2 minus log 18 base 2. Right? Now we can divide them, but before I do that, I am going to apply that power law again and put that 2 as an exponent there with the 12. So really, this is going to be log 144 base 2 minus log 18 base 2. Right? So now that you're subtracting logarithms with the same base, you can do a division where 144 divided by 18 is 8, and you're left with log 8 base 2. And now we evaluate that, which again, you're asking yourself, 2 to the power of what
3.
equals 8? 3. So this whole thing would evaluate to an answer of 3. Okay? So that's how you're applying logarithms to help you simplify expressions. Okay?
What do you do if it's like not the same base?
If the bases are not the same, you are not able to apply these logarithms.
You can't like make them the same.
Nope. You can't make them the same. Nope. You are stuck. Okay? So again, let's just try another one with simplifying, but now we're back to variables. Which one do you want to do? A or B? We won't do both. A? Okay, let's do A. So if we're going to simplify this, we've got log x squared base 7 plus log x base 7 minus, well, really we can write this as 5 over 2 log x base 7. You okay with that rearrangement of that term there? The fact that 5 log x base 7 divided by 2 is just the same as a coefficient of 5 over 2? Right, multiplying something by 5 and then dividing it by 2 is the same as just multiplying the whole thing by 5 over 2. Right, so again, we're just applying these laws. So these first two terms, right, they're being added, they have the same base, so I can multiply them. So this would turn into log of x cubed base 7. And again, with this now as the coefficient, I can apply it with that power law and turn it into the exponent. And now this is log x to the power of 5 over 2 base 7. Now I'm subtracting logarithms.
Multiply them, you add them, or you multiply them.
I multiplied the arguments here, x squared times x. X squared times x is x cubed. So when you're adding logarithms, you multiply the arguments, but when you're multiplying powers with the same base, you add the exponents. It's that reversal. So you got to really be careful with what are you dealing with. Am I adding logarithms, which in this case you are, but then the arguments of your logarithms have exponents, so then you still have to apply the exponent laws inside the logarithm laws. It's all combining together. No, x squared times x is x cubed. Right? And then this is applying that power law. So now we're subtracting logarithms with the same base, so we can divide the arguments. So this is now log with base 7 x cubed divided by x to the power of 5 over 2. How can I simplify that? How can I simplify that argument of x cubed divided by x to the power of 5 over 2 to make it look a little bit nicer?
You cancel the x.
I can't cancel the x's, no, but I can apply my exponent laws. Again, it's these exponent laws within your logarithm laws. You have exponents, right? They have the same base, they're both base x. What do you do with exponents when you're dividing? You subtract. You subtract the exponents. So what's 3 minus 5 over 2? 1/2. 3 is the same as 6 over 2. 6 over 2 minus 5 over 2 is 1/2. So we're left with log of x to the power of 1/2 base 7. And if you wanted to, you could then apply that power law again and switch that to just 1/2 log x base 7. All right, so you're just using all of your mathematical skills and tools at this point. Now you've just been introduced with the logarithms, and you're still applying your exponent laws within your logarithm laws themselves. Okay? So that's what's going on there. Let's take a look at a word problem that might deal with logarithms. Okay? So in this case, we're going to look at a word problem that involves a logarithmic scale. Right? Specifically talking about decibels. Okay? You guys have heard that any noise measurement is all measured in decibels, correct? Okay? So last week we kind of talked about how the Richter scale, right, earthquakes, was based on a logarithmic scale with magnitude, right? And it's all 10 times. Okay? It's similar here in decibels. Okay? So the intensity level, we're using beta for this, in decibels of a sound is defined by this equation. Beta is equal to 10 log I over I naught, where I is the intensity of the sound, right, which is measured in watts per meter, watts per square meter, and your I naught has a standard value of 10 to the negative 12. Okay, so I naught is constant in this case, and I is going to be the intensity of your sound. And that 10 to the negative 12 is the faintest sound that can be heard by a person with normal hearing. So that's kind of like your base level. The smallest possible sound is that 10 to the negative 12. Okay? So audiologists recommend that people should wear hearing protection if the sound level exceeds 85 decibels. The sound level of a chainsaw is about 85 decibels. The maximum volume setting of a portable media player with headphones in is about 110 decibels. How many times as intense of the sound of a chainsaw is the maximum volume setting of the portable media player? So we've got a decibel reading of the chainsaw at 85. We've got a decibel reading of your MP3 player at 110. How many times more intense is that? Right? This is not a linear scale. You don't just say, oh, it's this many more decibels more intense. We're talking about actual intensity of the sound. So we have a formula that's given us how to measure the intensity. Right? So I use my formula. I've been given the decibel value of 85. Put it in for beta equals 10 log I over 10 to the power of negative 12. I'm going to solve for the intensity there. Well, how do I do that? How am I going to go about trying to solve for the intensity in this case? I've got 85 is equal to 10 log, and this entire thing is the argument here. It's the first thing I'm going to do. Trying to get I by itself.
Fraction.
I would divide by 10 first, yeah. divide both sides by 10, and then we get 8.5 is equal to just log of I over 10 to the power of negative 12, right? You could then use that law of logarithms to break this argument up into two different logarithms. Because it's a fraction, I can turn it into two ones being subtracted from each other. So I can have this 8.5 is equal to log I minus log of 10 to the minus 12. Well, this second term here is just, you can evaluate that. It's all numbers. I can actually go on a calculator and say, okay, what is log of 10 to the power of negative 12? But common sense should tell you that that answer is just going to be negative 12, because your base is 10. 10 to the power of what equals 10 to the negative 12? Negative 12. Right, so what you end up getting here is this 8.5 is equal to log I minus negative 12. So then we would just add, well, I guess that really turns into a plus 12 anyway. So then it's subtract 12 from both sides. So your 8.5 minus your 12 would give you negative 3.5, which is equal to log I. And when you're solving for that argument, you switch your logarithms back into exponential form. So that means that I is equal to 10 to the power of negative 3.5. Okay, so the intensity of the chainsaw is 10 to the power of 3.5. But I am not near done, because that's just evaluating the intensity of the chainsaw. Now I need to evaluate the intensity of the media player and then compare the two to see which one is more intense. Right? So if I do that here, I'm going to do the exact same method in which I have the media player whose decibel level was 110 is equal to 10 times log, right, and that argument. And then, but I'm just going to go through those same steps again. Right? So first step, divide both sides by 10. So this becomes 11 is equal to log of I over, doing some recognition there, right, over 10 to the negative 12, okay? Same thing again, split up that logarithm, which is equal to log, okay, so equal to log I minus log of 10 to the minus 12, which once again, we've already identified that as negative 12. So subtract 12 from both sides. That's now minus 1 is equal to log I. So then the argument I is equal to 10 to the minus 1. So your intensity of your chainsaw was 10 to the power of negative 3.5. The intensity of your media player is 10 to the negative 1. So how many times more intense is the media player? So you're going to take your intensity of your media player and divide it by your intensity of your chainsaw. Again, these are both powers with the same exponents with the same base, right? So you can subtract your exponents, negative 1 minus negative 3.5. That's where you're getting that 10 to the power of 2.5, which when you evaluate that is 316.23. So a decimal changing from 85 to 110, while you might look at it and be like, oh, it's only like, 30 decibels in the difference, it's actually 316 times more intense. Okay? So that MP3 player with the headphones in at full blast is 300 times more intense than just the sound of a chainsaw. Right? In terms of impact on your eardrums.
Why did you divide them?
Because it was asking me how many times more intense something was. So when you're talking about how many times more, you do a division between the two. Right? So it's like if I had an 8 and you had a 2, how many times more than you do I have? 8 divided by 2, I have 4 times as much. Right? So that would be kind of what's going on there. Okay? We're just going to look at this part B of the same question and then we'll be done. Okay? So here, sounds that are at most 100,000 times as intense as a whisper are considered safe. All right, so that might seem crazy, right? 100,000 times as much as a whisper. What decibel level is that going to be? Well, we've already seen that the way that this decibel system works, right? A decibel change of about 35 decibels ends up being like 300 times as intense, right? So we have to kind of look at it in that sense. So if the level of a whisper is 20 decibels, what sound level in decibels is considered safe? Okay, so again, we can figure out, well, what is the intensity, right? Find the intensity of the whisper, do 100,000 times more than that, and then use that value in our equation again. So same method here, right? 20 divided by 10 is 2. Equals log of I over 10 to the negative 12. Split that up. Log I minus log 10 to the negative 12. So that's 2 is equal to log I minus negative 12. So we're really just subtracting 12 there. So negative 10 is equal to log I. So I is equal to 10 to the negative 10. So that 10 to the negative 10, that's the intensity of a whisper. The questions told us that intensities 100,000 times as much of that are still safe. So you can take that intensity of 10 to the minus 10, multiply it by 100,000, and what do you get? Right, well, you can turn 100,000, first of all, in 10 to the power of 5. Right, make that easier. So you've got 10 to the negative 10 times 10 to the power of 5. And then you can just add your exponents together. And you've got 10 to the power of negative 5 that's considered a safe intensity. Okay? So we've now figured out what the intensity level is for a safe intensity. And it's asking specifically what decibel level is considered safe. So we go back to the formula we were given, in which your decibel level is equal to 10 times log of I over 10 to the negative 12. And this time we actually have a value for I that we substitute in for I.
What do you measure I with?
I is measured in watts per meter squared. Yeah. So, no. No, you're fine here. So this would be log of 10 to the minus 5 over 10 to the minus 12. Okay? So again, apply your exponent laws. What's 10 to the minus 5 divided by 10 to the minus 12? So it's negative 5 minus negative 12, or negative 5 plus 12, which is positive 7. Right? So then if you were to actually evaluate that, you go to your calculator and you would do what is log of 7 times 10. And you get, oh sorry, this is 10 to the power of 7. Sorry, that's my mistake. So log of 10 to the power of 7, and then multiply that by 10. So this is actually 70.
Something like 70 decibels.
So 70 decibels is considered safe at no matter how long you listen to it. Right? So if you're listening to something at 70 decibels for hours and hours and hours on end, they're considering no damage is being done to your eardrums. However, anything over that, after a certain period of time, damage is starting to be done. Is essentially what you're dealing with there. Okay? So that's using laws of logarithms to help you solve equations that involve logarithms. Okay? And these are the practice questions we will now work on to practice these skills of our laws of logarithms.